So having bandied around this word for a while, let me try to explain what it means to do an approximation turbo. And you probably have guessed this because the name is somewhat aptly chosen. Right? What is an approximation? So in many of the problems we've looked at, the goal was to find the best something. You want to find the minimum spanning tree, the minimum vertex cover. Try to find the best of something. Right? So let's say I have a problem P. I have some problem P and I have some instance. Right? So it's an instance of the problem. So a particular graph, a particular set of numbers or whatever. And I want to find the optimal solution. We'll ignore for now whether it's a minimization or maximization. It doesn't really matter. We're just thinking of optimality. And if you want, just think of this all as minimizing. There's no real difference one way or the other. And so we'll denote this optimal solution as we'll call this is called number opt, and we'll a particular graph. Vertex cover is a set of vertices, or in this case, it will be the size of the set of vertices. It will be some number. And you want to compute this one. And often you can do it, or it's hard, or whatever. The idea of an approximation is that you want to say that you will always get close. Especially this idea of getting close to the right answer is pretty familiar to you all. You solve it, you engineer some heuristics, and you get some answer, and you do some experiments, and you say, okay, this looks pretty close, within 5%, 10%, that's good. But what we want to do here is a bit more ambitious. What we're saying here is that we don't just want to get close to the answer, we want to prove that we're always close to the answer, in the worst case. No matter what your instance is, we're always good. So of course the first thing to say is, well, what does it mean to get close to the answer? Okay. And there are two possible ways you can think about it. So let's say I have some algorithm A, and again the algorithm can run the instance. So let's say this is the cost. So this is the optimal solution. And let's say the algorithm runs and gives me some number A, okay? And let's say we're doing a minimization, right? So we always assume that A is going to be greater than or equal to opt for a minimization, right? Because you can't do greater than opt. So one these are numbers after all, is to say, well, let's look at the error is equal to E minus opt. Right? If the error is 0, I'm optimal. If the error is more than 0, I'm further away. The larger the error, the worse it gets. And that's kind of what we want. We want a number that gets bigger as we get worse and gets smaller as we get better. So this is a perfectly reasonable number. And if you want to sort of make this agnostic to max versus min, you might instead say something like this. Just so you can write it. And this error is sort of well known. It has a name. It's called absolute error. Okay. You'll see why. The solution. I will measure it by taking the difference of the two things. And then I can say something like, okay, what I want is to look at the error of it. So this is the error of a solution. How might I define the error of an algorithm? So, I mean, I ran the algorithm in a particular instance. I got an answer. I subtracted from opt, and I get the algorithm. But I want to say something about the algorithm, right? We always like to talk about the algorithm, not about a particular solution. What might I say? Sorry? Yeah, Charlie?
The maximum possible absolute.
So is that what you're going to say about it? Were you going to suggest a different method? You already had that.
I was going to say like average. Okay,
good. So there are two ways you can look at the average error, which is in fact a very common way to measure error in machine learning. We'll get to that in a second. So let's first take the maximum. Since we're used to worst case analysis, we might say something like, the error of the algorithm is equal to the max over all I of AI, and let's just write the subscript so we know what it is, minus opt. Right? So this is the error of the entire algorithm. And now we can say things like, okay, the error of this algorithm is 3, or 2, or 1. which case stop. But we now have a way to talk precisely about the quality of an algorithm, even when it's not getting the right answer. And that's important. Because if I was going to talk about approximations and guarantees, I need a way to measure how good. The idea of an average is a very good one too. For example, you could say something like the error, and I'll write this here, is equal to the, let's say, the expected value. And if whenever I say expected value, you have to say, but from what distribution? And so there's some distribution that the inputs are being drawn from. And I can do that. And like I said, if you do machine learning, this kind of measurement is very, very common. And there are other versions of this you can compare as well. We won't actually be considering that notion of average error at all, because we prefer to think about things in the worst case fashion. But it is a standard notion. Yes?
What about a relative error?
Coming.
Okay.
So this makes sense that I can now measure the quality of an algorithm, even if it doesn't get me the correct answer. And I get a number that gets larger if the algorithm is worse, in the worst case, and it gets smaller if the algorithm is better. Okay? And what I like to do is to say, you tell me what epsilon you want. You want to be within 5 of the optimal solution, and I will design an algorithm that can do it for you. That won't always be possible, but I can try. Okay. All right. And as was just mentioned, there's a third way, which is in fact the most common way that we think about error measurement in algorithms, which is defined this way. So here we'll now define epsilon al is equal to the max as before over I of, oops, sorry. You divide the algorithm by the optimal solution, and you get relative error. Now, both absolute and relative error are relatively common in the world of approximations. The relative error measure is more common. There are reasons, there are pros and cons of both methods of measuring error. One advantage of relative error is that in some sense it's scale-free. If you artificially make your input size double, let's say taking a graph and duplicating or something, the relative error won't change, the absolute error will change. The advantage of absolute error is that if your optimal solution can be 0, then you really don't want to have to measure that kind of quantity. It makes more sense to look at additive error. So there are different situations where you might choose one versus the other. That tends to be more friendly to use algorithmically, but they're both important. But the message here really is that there is a way to measure how close I am to the optimal solution, and I can look at that overall possible instances, and I have a number. Just like running time or something else, I have a number that captures how good it is. And so an algorithm is an approximation algorithm with approximation law, if I can produce something that has error law, in whichever notion of law you want. Any questions?
Is it an additive error also, or the absolute one is called the additive error?
It's the same thing, yes, because it's often used that way. And this could also be called multiplicative error. Yes.
Maybe just a little clarification on the use of epsilon. So when I've seen that used in mathematics, epsilon always seems to suggest something really, really small, such as something substantially less than 1.
And you are correct. And I shouldn't have written this as error as epsilon. I should have written this just as error.
But I've seen that in our paper, and I think I've been confused by that too.
Right. So usually, okay, in the relative setting, you will usually write an E of algorithm as 1 plus epsilon. So the ratio is, say, 1.05. You're always within 5% of optimal. So the epsilon will be 0.05.
Okay.
So that's usually, and you're absolutely correct. I should not be using epsilon to denote large quantities, even though the length technically wrong. That's how the concept is used.
Okay,
Epsilon.
thank you.
So correct, yeah.
And do we need to know like why is it 1 plus epsilon times this, or is it like something which is stated that way?
Sorry, I
How
understand the
did-
question.
So you said like E of algorithm is
The ratio
actually-
of these things, yeah.
Yeah, so it's 1 plus epsilon.
So for many problems, you can say that you can write out that ratio of 1 plus epsilon, because you're trying to say that you can get a pretty good ratio, and all that really matters is that tiny epsilon. And you'll see why in a second, because oftentimes the running time of your algorithm will depend on that epsilon. So instead of saying right, it depends on C minus 1, you just reparameterize it and say, okay, it depends on epsilon. It's just a convenient way of writing it. And also then you can see, okay, epsilon goes to 0, that means you get better and better and better, because the ratio becomes 1. Right? For these things, it actually does make sense to say epsilon, because that number you want to be small. Whereas there, it's a ratio, so the minimum value is going to be 1, not 0. So that's why you use the 1 plus epsilon, so then epsilon goes to 0. It's just a way to parameterize things so that going to 0 means good. That's all. Obviously, if your error ratio is 500, then 1 plus 499 is not very interesting. So it only makes sense now. Any other questions? So the reason why we do these things is, and I'll show you some examples of this, is because if you're willing to not be exact, if you're willing to get an answer that's close enough in this sense, but is not optimal, then you can do surprisingly well. You can bring down the runtime by a huge amount. So for example, you might have an algorithm that runs in n squared time. And n squared is horrible because you have lots of data, and n is a billion, and n squared is just not feasible. And then I come in and say, no, you use a special trick, and your algorithm runs in constant time by sampling. You sample a constant number of elements, and you do something with them, and you get an answer. So now your algorithm runs in literally constant time. It doesn't even look at the whole input. And it gets an answer which clearly cannot be the exact answer. It just doesn't seem right, but it can prove it's an approximate answer. So you can have a big win. So just like with randomization, you can often improve the running time by allowing yourself to toss coins. With approximations, you can often improve the running time dramatically by allowing yourself to not be exact, to not be perfect, to be good enough, but in a provable way. And before I go into the examples of how this works, I'd like to say a few more things about what makes it hard to show these things. Because if you think about what you're having to do here, you're having to reason about how close the algorithm is to your optimal solution. And I want you to think about that. We don't know where to find the optimal solution. We're trying to get it close to it, but we have no idea how to do it. And yet, I'm being asked to reason about the optimal solution itself. And that's kind of tricky. When we look at greedy algorithms, you saw the same problem, that we're trying to reason about why the greedy algorithm is optimal without knowing what the optimal algorithm is actually doing, without being able to make any kind of assumption on what it's doing. And so the usual paradigm with approximations is that you do the following thing. And again, let's stick to minimization for now, it's just easier to think about it. So let's stick with minimization, let's stick with relative error. Okay? So we want to show that, that for every algorithm, the max over all I of AI, I have an extra parenthesis, I don't know why, of I is less than equal to some constant. Right? We want to say this ratio is bounded. Maybe the C is 2. I'm always within a factor of 2 of the optimal solution. I'm at most 100% error. So now, I don't know what opt is doing. Usually this could be a tricky problem to solve. How do I reason about this? And so what I do is, I try to think very hard, and this is the hard part, and try to come up with what I'll call a lower bound. Not a lower bound for an algorithm that we just saw, a lower bound on opt. L, such that for all I, the lower bound on I, that's why it's called a lower bound. Try to find some property of your input, that some number you can find from your input that's always less than the optimal solution. That's something you want to handle. Suppose I can do that. So that's step 1. Then step 2 would be prove that for all I express your algorithm in terms of the lower bound. So why will these two statements together prove what you want? Well, we just said the lower bound is less than the optimal solution. So that's why we call it lower bound. We prove the algorithm is no more than C times think of C as a big number, like 10, right? It's no more than C times the lower bound. But the lower bound was less than optimal. So the algorithm is no more than C times the optimal. And we're done. Which is what we want to prove in the first place. So thinking about approximation again is this kind of backwards way of thinking. We're not thinking about the algorithm itself. What we do, well, we have an algorithm, but we're trying to reason about design some kind of lower bound that we can then reason about it as well. Yes.
Are you talking about cost here, or are you talking?
Yes. Cost. Always about the value, the number. All these problems have number.
Before you were talking about solution, right?
No. The solution is a number, like the size of the vertex cover.
Oh, okay.
The most frequent item in a set. These are numbers, always numbers. Otherwise, it doesn't make sense to talk about approximation. And again, we'll see examples. But this is the basic template for pretty much every approximation algorithm. You need some notional lower bound. Again, for minimization, it's a lower bound. For maximization, it's an upper bound. But you have to sandwich it something. And then you relate your algorithm behavior to this proxy for the optimal solution. And then prove it works. And so your bound is controlled by two things. How clever you are at proving this step. And how clever you are at proving that step. If your lower bound is terrible, you won't be able to prove the bound here. Like if your lower bound is really below optimal, like well, every vertex covers a size of at least 0. Haha, that's my lower bound. Yes, it is, but it's not very useful. Because it's so far below anything that every algorithm is going to be infinitely larger than the lower bound. And this number is going to be infinity, and you really have that range. So the art of approximation is proving a lower bound that's close to your optimal. It's a very good proxy for it, and then reasoning about that. And diagrammatically, if you think about it, this is my optimal solution somewhere here. On a vertical scale, my opt is larger. This is my opt. And this somewhere up here is my algorithm. I want to reason about this gap. But instead, I'm going to reason about this gap. And since this gap is more than this gap, if I give this an upper bound of this, I give an upper bound of this. But obviously, I don't want this to be way out there, because then my upper bound is going to be huge. And that'll be a very poor proxy. And for a maximization, just flip this whole diagram upside down. Okay? So that's the high-level picture. Now let me give you an example, which is, I think, a nice example to sort of see how this works. Okay. Any questions for anyone? So let's look at an old favorite. I know it should be an old favorite. Vertex cover. Hopefully you all know what Ramon's problem is. You're given a graph. You want to find a set of vertices that touch all the edges, and you want the set to be as small as possible. As you know by now, hopefully this problem is NP hard, which means we don't know if there's a polynomial time solution. I am now going to give you an approximation algorithm that runs in linear time. So here's my algorithm. Take an edge. So the algorithm works as follows. Take your graph, take any edge, pull it out, take both set points, put them in your set, your bag of vertex cover solution. Now you pick those two vertices. They cover all their neighboring edges. You don't cover them anymore, so delete them. Now you have a new graph. Do it again, and again, and again, do it that. So that all the edges have been covered. I claim that which means that okay. So, do you understand the algorithm? I'm not asking you to tell me if you think it's correct or not. Do you understand what the algorithm is doing? That makes sense to you? And do you understand the claim I'm trying to make? I'm trying to claim that it's a 2 approximation, and that's what it means. You always know the fact you know more than twice what the optimal solution will be. Okay.
Can you please explain why do you say it is a 2 approximation?
Sorry, just a bit of jargon. The word 2 approximation is a shorthand for that. That the ratio is equal to.
Yeah, even that like.
Oh, well, I'm going to do Y8. I'm just making the claim. There's no proof. But do you understand the claim?
Restate the claim one more time.
The claim is that for any graph, the solution I produce from this algorithm, the vertex number set that I produce, will have a size that is no more than twice the size of the optimal solution. So that's it. Okay. How are we going to do this? So I said I could produce a lower bound. So, out of just sheer inspiration, well, maybe not out of sheer inspiration, but okay, let's not do it the inspired way, let's do it the proper way. If you think of what the algorithm is producing, don't look at the vertices, look at the edges. What can you say about the edges that the algorithm makes? Can you say anything interesting about them? Think of, okay, fix an edge. That's first one is fine, just fix it. What about the second edge? What kind of relationship does it seem to have with the first edge?
Hops one edge.
It?
Hops, right? If I take one edge, I
Yeah.
won't take its neighboring edge.
But you said it's hops one, that means you will take something out of it?
I might take.
Okay, so maybe you're not saying one, you're just saying that it doesn't touch it.
It doesn't touch it here.
So the next edge does not touch the previous edge. What about the third edge? Then it does the first two. So if you start trying to picture what this looks like, it starts looking like this first edge we pick, the second edge. Does this remind you of anything? Someone said matching. Who said matching? Very good. It's a matching. It's not a maximum matching or a perfect matching or any kind of matching. It's a matching. And I'm going to keep picking edges till I'm done. At the point when I'm done, what can I say at this point? What is true about the graph at this point when I say I'm done?
Right? Is the vertex color?
No. Really? Can you say that? I can't say that. Not yet anyway. Something simpler. What can I say about this set of edges here?
They are not touching each other.
Yeah, that we said. That was always true. But what else can we say? So maybe I jumped too quickly on you. It's a vertex. Can you say more about what you're claiming about this being a vertex?
So by these nodes we have colored all the vertices.
All the edges. All the edges. Which means that every other edge in the graph touches one of these edges. Otherwise, I could have picked one. Right? What is such a matching called? Do you remember? This is back in the prehistoric era, many moons ago, when we talked about matching. I mentioned that this kind of matching is a name. It's not maximum, it's not perfect.
Flow problems.
Sorry?
Flow problems.
No, it's not a flow problems. It's a kind of matching. It's a something matching. Huh?
Just kind of.
Pareto matching? No, I didn't say that. It is, but well, technically it is, but let's hold it. It's a yes.
It's a maximum matching where you take it as many as you can, but you should go ahead.
Is that maximum? Not necessarily.
Maximal.
Maximal matching. It's a maximal matching, so we're very close, yes. So such a matching is called maximal because you can't grow it anymore, by definition. So this is a maximal matching. Okay. Here's a claim I'm going to make. Okay, by the way, the size of this matching is the number of edges in this matching, yes? If I had to run out of a vertex cover in a graph that looked just like this, nothing else, how many vertices would I get? So the graph looks just like this, that's all. There's nothing else in the graph, just this. Half of the? 2 into edges. How many vertices do I need to cover all these edges?
Maximum divided by 2.
I need 1 vertex per edge. Right? Well, once I pick a 1 endpoint, I've covered the edge, right? There seems to be a rumbling of discontent here. No? Not happy with that claim? I need to pick both? 1 is enough, right? I've covered the edge. So the number of vertices required to cover this graph is equal to the number of edges in this graph, which is the size of this matching, right? But of course I have other edges in the graph. Now what changes the maximum matching size? Does it change the vertex cover size? Would it maybe make it bigger if I have to add more edges, if I have to cover more edges? It might, right? It certainly won't make it smaller if I throw in more edges into this graph. And more vertices. Yes?
What do you mean by throwing more vertices?
So I'm doing a thought experiment. I had my original graph and I picked up these edges. Now I reverse it and say, okay, suppose I only had these edges and I now throw in the other edges back.
Okay.
Then my vertex cover size cannot go down. Because adding more edges means more work for my vertex cover, just to cover more stuff that it hasn't necessarily covered before. Right? In other words, the claim I'm sort of circling around the drain here to get to is the following. The size of a maximum matching is a lower bound on the size of a vertex cover. That's what this claim is saying. That since you have to cover there is no way to cover 2 edges of the maximal matching by 1 vertex because they're disjoint from each other. Every edge needs its own special cover. So the number of vertices in your vertex cover is at least the size of this maximal matching. I'm not saying it's more, but it's at least the size of this. And that's a lower bound right there. We have now produced a lower bound on the vertex cover in terms of a matching in the graph. And this would not be interesting except for the fact that we can immediately make a second statement. That the algorithm why? Because what did I say the algorithm does? It picks an edge and takes both endpoints. 1 edge, 2 vertices. 1 edge, 2 vertices. 1 edge, 2 vertices. So actually should be equal. So we've just observed 2 things. First of all, that the result produced by the algorithm the edges we pick up and that we take both endpoints of happens to be a maximal matching. And then we observe that, wait, a maximal matching is a lower bound of the size of a vertex cover. These are the 2 things we needed. We needed a way to relate something to the optimal, and we need a way to relate our algorithm to it. We put these 2 things together, we conclude immediately that We have a 2 approximation to the vertex.
Would it always be that we use the same algorithm for the answer and the approximation, or would it be?
I don't understand.
So for you created the lower bound using the solution of
The algorithm.
maximal matching, right?
Maximal matching, yes. But that's because that's what the algorithm was doing. Usually you have this complicated dance where you design the algorithm, it does something, you try to analyze what it's doing in terms of the optimal. You fail, but you come up with some ideas, and you go back and change the algorithm. And you do this back and forth for a while. Eventually you come up with an algorithm that's doing something, and a lower bound constructed via what the algorithm is doing that you can reason about. And then you put them together. So it's not like, it's a chicken, there is a chicken and egg problem here. You sort of do the both. Yeah. A little bit of chicken, a little bit of egg, a little bit of chicken. That's a solution to the question.
Sorry, how do you prove that AD is less than 2 times of maximal matching?
Because for every edge in the maximal matching, the algorithm says take both the inputs. 1 edge, 2 vertices. 1 edge, 2 vertices. 1 edge, 2 vertices. So the maximal matching is size k, I'm picking 2 k picks.
Is it equal or it should be less than?
Yeah. Because I'm a lazy theoretician. This is why I write things like this. You're right. Okay. This is an example of an approximation. I've been able to prove to you that I can always give this factor. This is a very old algorithm, one of the first approximation algorithms so many decades ago. To this day, we don't know if we can do it better. We don't know if there's anything better than this. I think there's tiny little improvements that are sub-constant improvements, but really, for all practical purposes, there's some reason to believe we may not be really better. But not yes?
Why is the algorithm doing 3 times the maximum match?
Because, let's go back to the algorithm.
Could you possibly remind us of maximal, or how you would do maximal matching?
This is in fact how you compute a maximal matching. Take an edge, take another edge, take another edge. Keep taking edges till you can no longer take an edge. By definition, it's maximal. See, a maximal matching is a very weak object. It's not promising anything. It's just saying, I can't grow any further.
And then maximal matching would be a set of edges.
Yes.
And you also said when you said vertex coverage.
But one second, let me get back to the question. So the reason why it's factor 2 is because the maximal matching size is the number of edges in the matching.
Oh, got it.
That's why, exactly, yeah.
I see.
Yes.
Did you also mean the minimum vertex covered here or
Yes.
anywhere?
So if we could establish any relation between the maximal matching and vertex color, for example, we could say that some nodes in the maximal matching are the nodes that create the vertex color. Then we could solve that. Yeah.
If your graph is bipartite, there you go. If the graph is bipartite, then the maximum matching is equal to the vertex cover. And you can therefore solve vertex cover in bipartite graphs in polynomial time using flows. So the answer to your question is yes. In that case, you can do it.
But generally,
Well, we don't know. Except we are. But for bipartite graph, you can. Questions? Okay. Let's take another example. And this is not a problem that's actually particularly hard to solve. Like, why on earth should I ever want to produce an approximation algorithm for median time? We can do this in linear time. You have this wonderful decimation algorithm that can do this for us. But suppose I want to say that not only can you do it in less than linear time, you can do it in constant time. I can do it without even looking at all the input. Then maybe I'm willing to talk. As long as I'm willing to be a processor. So consider the following algorithm. So I should say that median finding is not a problem where you want to find the optimal solution. You just want to find the solution. So what does it mean to approximate median? So let me first define the notion of an approximate median. So we can think of the median. So the median has rank n over 2. If you think of the order list. Let's think of it as having, let's say that has what we'll call fractional rank half. In other words, the rank divided by the total number of items is half. So the fractional ranks go between 0 and 1. The min has fractional rank 0. The max has fractional rank 1 minus 1 over n. Or okay. So when I talk about an approximation to the median, I'll say a sort of a C approximate median. We'll call it M hat. Is such that it's close to the actual median.
Can you repeat what you mean by maximum?
Sorry?
Can you repeat what you mean by maximum rank?
Rank divided by n.
Rank is the position in the matrix when you solve.
Yeah, so median has position n over 2 in the sorted list. So what I would say is that my rank is not going to be half. It's going to be kind of close to half. And the reason I want to divide by n is to make the scale freeze. So I'm going to talk in absolute, in sort of in terms independent of n, right? So you can think of this as being, I'm within, 5% of the median. So this would be 0.05. Okay. So this is what I define as my C approximate. So here's my constant time algorithm to compute an approximate median. This takes 3 time units to solve the problem. Not n, not log n, not square root n, 3 or 4 if I'm being slow. Constantly.
What is the
I claim, look, all the questions. I claim this is an approximate median. And I claim it's not even that bad of an approximate median. What do you think?
have a set of 3 in this list.
Sorry?
If your size is 3, it'd be a great approximation.
That's true. So it's a great algorithm for 3. Sadly, I don't have 3. I have 1 trillion. Now what?
for any distribution?
Yep. Yep. Yes, I'm cheating. I'm using randomization and approximation. Who knew? They tend to go together. It's like peanut butter and jelly. Randomization and approximation always go together. If you have a nice randomization approximation sandwich, it's very, very tasty. Highly recommend. They don't taste as good apart from each other. Especially in the big data sandwich. So yes, so what do you think? What do you think is going to happen? First of all, should it make sense? Is there any reason why this might be a plausible algorithm? Or am I just being crazy? Or both? Yes?
The other thing to think of is, you're talking about adversary trying to defeat the algorithm.
Yeah.
And like with this, I can think of ways to defeat this algorithm so you have an approximation that's way off.
Defeat it.
The median.
Do it.
You have a distribution that's
I get to pick the
random.
randomness. I'm the algorithm.
Yeah, but he's giving a distribution of the input, right?
The distributed input is random, and so you get a couple ones that are way off, and so you get a median that's way over here, even though the median's over here.
Wait, so what does my input look like? Describe my input.
It's lopsided.
So
Instead of being uniform, it's
Yes.
lopsided.
yes.
So you get a median.
So what does lopsided mean?
It's forget the technical term, but it's all one end,
One end of what?
the values of the numbers.
But I don't care about the values. Do I? Am I looking at the values at all?
Not doing the mean.
I'm not going to mean.
Median.
Median.
Okay,
I would not make this claim about the mean. This would not even be true.
okay.
Well, actually it is true. If you take a sample of the numbers and take the average, that is in fact an expectation the mean of your subject sample. Its variance is horrible. So we don't mean that. We build it for your kinds of examples. But for the median, I'm not doing that claim at all.
Okay.
Yes?
So you get to pick the randomness for this algorithm. If you were to tell us the random algorithm, we could.
I'm not, it's random. I don't even know it myself. I would love to tell you, but I don't have a point.
Okay, so assume that we have the first three elements are 1, and the rest are 2 billion, and randomly you put
The rest are all 2 billion.
2 billion.
Okay.
And
So wait, what's the median of this?
what was that?
What's the median of this input?
Somewhere between. I don't
No,
know,
it's 2 billion.
1 billion.
It's 2 billion.
2 billion.
If they're all 2 billion, it's 2 billion. And if I pick 3 numbers at random, they're most likely they're going to be in the 2 billion.
But randomly, if you were to choose the first 3 elements,
That's not random. That's Dilbert random.
it's a really bad, but it's possible. You could choose.
It's possible, but is it probable? We're talking about a randomized algorithm. As I've told you before, you don't talk about possibilities, you talk about probabilities. My claim of goodness is going to be a probabilistic claim. With some probability of error, I will guarantee that you'll have a good approximation. But that's all I'm going to claim. It's a randomized algorithm. I don't make absolute claims for randomized algorithm. But good, that's good thinking. But that's how I want you to think about it. So why? So I mean, you're doing the right thing. We're trying to find out ways why it won't work. Let's try to switch back and think, why should this even work? Is there any conceivable reason why this should work? I mean, based on the sort of current failure of these counterexamples, what might you be thinking? Yeah?
Even if you have if you have an extremely large set of data, the chances of you getting, say, like picking the 3 largest elements all at random are extremely small.
Okay, good. Under what conditions? I hear, oh, well, that makes me happy when someone says that. So, under what conditions will this work? Where do you have to pick your elements for this to work? So, imagine the following. Think of your input as divided into 3 chunks. Okay? So, let me go to the next page. Imagine the input here. And don't think of this as a real line. Think of it just as the ordered list, okay? Not the values, the ordered list. So rank 1, rank 2, rank 3 up to rank n, okay? And divide the 3 chunks, everything up to rank, fractional rank 1/3, everything from there to 2/3 in the top. Okay? Under what condition would you give a wrong answer? So one condition under which you give a wrong answer is if you have too many things in this section. If you have 2 things in this section here. If you have 2 items sampled in the section here, your median is going to be the lower one of those 2. Because only 3 items overall, right? And then that'll be a bad answer. It's very far away from the middle. If you have 2 items in this section, again that'll be a bad answer. But if you have items picked on either side, then your middle item is going to be somewhere in the middle here. This is very hand-wavy, but this is kind of the intuition behind what's going on. Yes?
Where's the C in respect to all this?
C is going to be something like 1/3.
Okay, so we should put it right.
Yeah, so I mean this is the error basically. If you really want this, right?
Right.
So there's going to be some error around it.
Right.
Yeah. So the intuition here is that if you make your approximation interval sufficiently large, then the probability of picking lots of stuff on the one wrong side on the other wrong side is small. In this particular case, the probability of picking 2 things from the top side is basically 1/3 times 1/3, which is 1/9, right? Because both of them have to be picked in the top section. Correspondingly, the probability of picking 2 things on the bottom side is 1/3 times 1/3, which is 1/9. Either of these 2 bad events could give you trouble. So the overall probability of error is 2/9. So with some reasonable probability, roughly 1 minus 2 over 9, you will get a balanced set and you will get an answer which is kind of okay. So my approximation error is quite big, right? It's 1/3, it's a lot. But that should suggest something to you. a way to fix that problem. Why did I pick that error to be 1/3? Essentially because I had 3 elements. If I pick more elements, I can actually try to make this bound even smaller. Because then the chance of picking a whole bunch of stuff on one side starts going down. Right? The chance of picking 1 on one side, okay. 2, okay. 3, 4, 5, 6, 7, that seems a little less likely to get a huge skew on one side. And in fact, in general, if I say that I imagine dividing up my range, and I have my median, and I have some range around the median, so gap epsilon. For any epsilon, this is where the epsilon is going to come in. Okay? I claim that if I sample roughly 1 over epsilon elements and take the median, I might need something like 2 over epsilon, but that's okay. Then the answer is epsilon approximation with probability something like 1 minus 1 over 2 to the 1 over epsilon. It's a very large number. Intuitively, what's going to happen is this. You have a bad situation here. So if you're sampling 2 epsilon elements, you have a bad situation if more than more than half of these elements appear on one side, or more than half of them appear on the other side. Right? Otherwise, you have a balanced sampling on both sides. Okay? Now think of this as a slightly biased coin. An unbiased coin has a probability half of being on one side of half. A slightly biased coin has a probability of little less than half of being a little bit further away from half. In that region of length half minus epsilon over 2. Okay? So what we're saying is that, and let me just go to the next page here, the probability of k elements being in the range, and this is all the fractional rank range, these are not values, this is the fractional rank, right? From half plus epsilon over 2 to 1, and this is an interval of length 1 minus epsilon over 2. The probability of them all being there is something like 1 minus epsilon over 2 to the k. And then you similarly want k elements on the other side. That could also be a bad case here. Right? And now you want this number to be small. And if by now you should remember that if I see a 1 minus epsilon inside, I want to raise this to 1 over epsilon to make sure this number becomes very small. It becomes a very small constant probability. And so this tells you immediately that k should be roughly 1 over epsilon. So you need 1 over epsilon on one side, 1 over epsilon on the other side. So again, I went through this analysis very quickly, and this is not by any means a formal, rigorous analysis of what's going on. But the intuition here is that when you couple this ability to approximate, I have this little slush factor around the mean, around the median. It creates a little bit of a bias, and now you can exploit that bias by random sampling. Say I don't need too many random samples to get a nice balance structure. And the running time of this algorithm is 1 over epsilon. It is independent of n. Obviously, I can't set epsilon to 0. I can't get the exact median using this because epsilon equals 0 is semi to infinity. I have to sample a huge number of times. But that's not the point. The point is I can get arbitrarily close to the median, as close as I want, and spend constant time, as opposed to spending linear time. And that's a huge win. It's not like it slowly gets worse. It's like constant. Oh, of course, it's really a growing constant because of epsilon, but it grows very slowly. And that's the power of approximations, that you can dramatically reduce the time it takes to get even very, very close, as long as you're willing to not be exact. Yes?
From this, can I repeat the experiment so that I can get a better approach?
That's what I'm doing. The 1 over epsilon is repetition. You can think of it as repeated random trials.
Okay.
That's what the analysis is doing. Yeah, and yes, you can repeat this. There are many tricks you can do to pile up repetitions of these things to do even better. If you've ever taken Jeff's, this models of massive data class, or if you will in the future, then he's covers some of these things in that class.
By repeating the experiment, can I also make the error lower, not just getting faster the error?
They relate to each other. The error and the approximation are connected. If you want a smaller approximation, you either pay a bigger error or you use more samples. So these 3 terms are all playing on each other. So you can fix 2 of them, and the third is fixed by them. So you have to decide what you want to fix. Either you fix the approximation of the error, then you pay a certain number of samples. You fix the approximate samples, you get a certain amount of error. Or you fix the error of the samples, you get a certain value. So they're not independent of each other. But you can choose which ones you want to fix.
So
Yes.
when you want to choose your sample, you don't know the position of them.
It's random. Exactly.
So why you say that if they shouldn't be in one section of that?
Because what I'm saying, I don't know what they are. But I'm saying is, when will my algorithm fail? The algorithm will fail if, when I make my random choices, it so happens that they happen to be in the area. But I can analyze the probability of that happening. I don't have to know whether it happens or not. I just have to look at the probability of this happening. So you can think of an outside observer who's watching what's going on. The algorithm designer, and it's doing the analysis. The algorithm doesn't need to know this. The algorithm just runs and does something. Right? It's oblivious to all this. It's again like every randomized algorithm. It's very simple. Sample, take the median, done. Then we go back and say, okay, well, what is the probability that it fails? Yes.
Would you just help me complete one thought here? So we're claiming this runs in constant time.
Yes.
But we're doing 1 over epsilon trials.
Which is constant. It doesn't depend on the input size.
That's all it needs to be constant, is independent of input size.
Yes. It is not, the running time is not whether I have a billion elements, a trillion elements, or terabyte, petabyte, whatever. It's the same running time. The reason it works is because my error is fractional, right? In absolute terms, the number of elements I could be off by is increases with n. But in fractional terms, my relative rank, I'm always within 10% of the median rank. That 10% is percent of a petabyte or trillion, whatever. So that could get bigger. But in relative terms, it's fixed. And that's why you can do these things. It's like polling, right? When you poll, the number of samples you need to get a certain error bound is independent of the population. It only depends on the amount of error you want. If you want a 3% error, you sample 1,000 people, right? That relationship is fixed. It has nothing to do with the population of the country. Whether this is India or the US or whatever, it's the same size, same sample rate. Yes?
I just had a question. Where did you get your 2 factor? Just one more time.
Which one?
The 1 minus epsilon over 2.
Oh, because because the total interval is length 1.
Sure.
The error, the place where I'm happy is epsilon.
Right.
The total length of what's left is 1 minus epsilon.
Yeah.
And it's symmetric, so there's 1 minus epsilon 2 above, 1 minus epsilon 2 below.
Right.
Right now, we're just analyzing the above case.
Right.
So the probability of getting something there is 1 minus epsilon over 2.
Sure.
And then, so that to the k, and then there's the other side to the k.
Right, but couldn't you get points in the 1 minus epsilon over 2 over here and over here, but still get a bad median approximation?
Well, the only way I get a bad median approximation is if I have more than half the elements in one side or more than half the elements in the other side. If they're balanced, then the median will be in the right range.
If they're balanced. Okay.
So I can analyze them separately. Yeah. Like I said, this is a bit fuzzy. You're probably right that there's some fuzziness in my reasoning, but this is the basic intuition. Right now, I'm sort of proselytizing, trying to convince you that you can do these kinds of tricks. In fact, write it down as a proof, then I would get 0 for the proof. So yes.
I don't really understand how the algorithms work. So every time you pick random points, right?
So the algorithm says, take your input, pick 1 over 2 over epsilon elements at random, compute their median, output that answer as the claimed median of the entire set.
So are you doing this once or are you doing this multiple times?
Once.
Oh, okay. Making sense now.
If I want to reduce my error, I can just take more elements, but always do this once.
Yeah.
Yes?
So how the chance of success change when we change the E actually works on? I mean, what is the chance of success of the C approximate solution when we change the C? Is there a formula for that?
It's kind of messy, but yeah, there's a formula. Yeah, it's, I mean, so basically, this is the probability of error. 2 times 1 minus epsilon by 2, roughly. So you fix this error that gives you a value for k for a fixed epsilon. So for any value of epsilon and any value of k, you get the error model. As I said, 2 of these 3 parameters are fixed, right? So if you set there's the error term, number of samples, and the approximation. So you can, if you fix any 2 of them, you get the third one. That's what I was trying to do. So this is very common in a lot of data analysis problems, that you have these 3 parameters: the complexity in terms of the size of the sample, whatever you need, the accuracy, which is epsilon, and the error, which is delta. You will often have things which have this epsilon delta being equivalent. Like you thought after taking calculus class you were free of epsilon delta, it's going to come back and haunt you right here. So this is a very common thing. So you've probably seen this in your paper. You mentioned, Juby, that your paper has approximations. It probably has epsilons and deltas in it.
Suppose that we have k elements and we want that approximation, E and the node can compute the error.
Yeah.
What is the chance of being in the range of that error?
No. The claim is that with probability 1 minus delta, the answer my algorithm produces will be in the desired approximation range. So think of it this way. For a randomized algorithm, I promise I am correct with probability delta. That's my normal randomized promise. Now take away correct and replace by approximately correct. So I promise that I am approximately correct with probability 1 minus. Okay. Any of you heard of path learning? It's probabilistically approximately correct, and that's kind of what's going on there. Like I said, they go together, right? Peanut butter and jelly. There's no, in other words, approximations is a the idea of approximation is a different concept, but in the world of data analysis, they tend, like I said, sampling and things like that tend to work very well. Okay. I was going to do another algorithm, but I think I'll start it now. I'll continue it next time. Here's a question that you may have heard. This is a classic tech industry interview question, because the guys haven't figured out, we already know the answer. We just tell everyone the answer, and we think it's very easy to solve. So here's the problem. I give you a sequence of items. So numbers, let's call them x1 to xn, they're coming at you, okay? And I tell you that one item occurs more than half the time. Strictly more than half, okay? So you think of the numbers as 1, 7, 2, 1, 7, 1, 1, 1, 2, 2, 1, 1, 1. So the 1 occurs more than half the time, okay? And you're given a box that can store one thing. You're given one box. That's your memory. You are very, very forgetful. Find the other thing. You're given one storage. You can store one thing. You can store one count or one identifier. Maybe you have 2 boxes. You can store a count and a label. That's it. And you define that element. That is guaranteed to be there. If you haven't seen this before, it will be very, very puzzling. If you have seen this before, it's like, well, yeah, that's the solution. Have any of you seen this before? 1, 2, 3. Okay, you're all forbidden from opening your mouth. Yeah, this is not the kind of problem where if you think about it long and hard, you'll get the answer. It's kind of a trick. So it's an that's why the interviewers love it, because it's a trick. It's also why it's a dumb question for an interview, because it's a trick. It's not as if it's not about being smart or figure out, it's just like knowing the trick. So let me, since we have a few minutes left, let me just tell you the answer to this, because I'm more interested in what it tells you about the problem than the answer itself. Right? The solution is very simple. Let's say it's basically, so you start off with an empty box, right? So you have an empty box, and let's say you have a label box for this. So the item comes in. So you store the first item. So the first item, you give it a count of 1, and you put the item label here. Okay. So now the next item comes in. Suppose the next item has the same label. Okay? Then increment the counter. Because you're just counting it, right? Okay? If it's not, subtract 1 from the count. Okay? If the count happens to have gone to 0, throw out that item and replace by the new. At the end, report the label. If you're thinking why the hell, then you're probably thinking the same thing I was thinking when I first saw this. Okay?
When should I throw away that?
When the count goes to 0. So let's take a simple example. So let's say let's come up with a string. So let's say we want 1 to be the most common. It's 1, 2, 7, 1, 1, 6, so 1, 2, 3, 6, 1. Okay? So this has 7 items. And 1 is most common. 1 has his count of 4. Okay? So I start off, my first box will be 1 and 1 is the label. Then I see a 2. So I subtract this to 0 and replace it by 2. I really hope this works.
No, it should be 0 to right?
No, I saw 2 once.
Oh, you saw 2.
Okay? Now I do it again. Now I see 7. Now I see 1 again. Now I see 1 again. Now I see 6. And now I see 1. I return 1. So that's what the algorithm is doing. The algorithm only promises to give you the correct answer if in fact an element exists. If no element occurs more strictly more than half the time, then it can give whatever answer it wants. So you can you could try that if you reorder these things and have 1 less 1, you might not get the right answer. Right? If you remove that 1 and put that in the system, you might get it. So this is by the way, and we'll continue this next time. This is a very simple case of a more general strategy for estimating the frequencies of items in a stream when you don't have enough memory to store all the items. Okay, so I want to count how many times different items appear in a stream. This is a very common problem. And there are many places where you want to do this, but I don't have enough storage to store all the possible items. Again, think of this like a hashing type problem. I'm counting all the different IPv6 addresses. I don't have 2 to the 64 buckets. But I just want to count the most frequent items, the most popular ones. This generalization of this idea allows you to get an approximation to that. In a situation where getting an exact algorithm would be impossible. And we'll continue the discussion next lecture. And I will see you all. Meet up.
You said I only need to turn it back in. You want me to turn the PDF into or am I just my appears in general? Like when we turn it in, like how we just generally, I didn't get it.
You don't need to sleeping. I probably don't have So I think, yeah, you're right.
Yeah, I'm always
I think also, I also prefer to everything I wanted to be more detailed about it, so I'll get that back to you. You don't need to return the what you corrected or anything with it. You don't need to say what you corrected or anything.
So at the end, I just turn in the PDF after I get your notes. Okay, great. I just wasn't sure if I had submitted it wrong.
Yeah, no, it's my fault.
Okay.
Yeah, it's a.
Well, I'm assuming you've got Avalanche, so I don't think it's your fault either.
It's partially my fault, but it's also the Avalanche effect, but it's also partially my fault. So I will. I need to take personally. So. Yeah.
So, final code submission?
the project. I believe so. I don't remember about the report. You probably want to ask. But
I was just wondering, like, I have a brother's wedding. I was planning to travel.
Okay.
So, like, our presence is required personally, or can I submit online?
I'm going to say you can always submit online. I don't think that Suresh will care. Go ahead and confirm with Suresh, but I'm betting he'll say it's fine. Yeah. To be honest, I mean, you're not the only one who travels like right at the start of December. There's a whole bunch of students that just start like a little
That's
bit
my first
early.
semester. I was wondering whether I should go before. Since I'll be traveling from 9th December, so before the term ends, I just wanted to.
Yeah, just turn it in. I'm fairly certain you'll be fine. And if not, I mean, people travel, so it's okay.
And by what time can you be giving us the final submission letter, like guidelines and what is expected from the draft?
The final report, you probably want to ask Suresh. Mostly I deal with homework, so
Sorry, Ben?
mostly I deal with the homework. So you probably want to ask Suresh about this report, the project guidelines. So
I'll do that.
Suppose the second element appears. Suppose the sequence is 1, 6, 6, 6, 6, 6, 6, 6. How do you know? You compared 1 to 6. Okay, suppose it was 1, 6, 1, 1, 1. You got